The universe, vast and silent, hides a breathtaking secret. It's not standing still. For most of human history, people believed the cosmos was eternal and unchanging. But we now know that space itself is stretching, carrying galaxies away from one another like dots on an inflating balloon. Even more astonishing, this expansion isn't slowing down, it's speeding up. The deeper we look into the cosmos, the faster galaxies appear to flee. This mysterious acceleration challenges everything we thought we knew about gravity and the fate of the universe. Why does it keep expanding? What unseen force drives this cosmic growth? The search for that answer has become one of the greatest scientific quests of all time. So watch this video to the end and subscribe to the channel. Let's start. When we hear that the universe is expanding, it's easy to imagine galaxies as tiny specks flying through empty space, like fireworks exploding outward from some central point. But that's not quite right. In fact, it's one of the most common misconceptions about cosmology. The galaxies themselves aren't racing through a pre-existing void. Instead, it's the space between them that's growing. The universe isn't expanding into anything. Rather, it's the fabric of the universe itself that's stretching, carrying everything along for the ride. To visualize this, scientists often use an analogy. Imagine the universe as the surface of a balloon. Not the inside, not the air, just the rubber skin. Now imagine small dots drawn all over that surface, each representing a galaxy. As you blow up the balloon, the dots move away from each other, not because they're traveling across the balloon, but because the balloon's surface, the space between them, is expanding. The dots themselves stay where they are on the balloon's surface. What changes is the distance separating them. That's exactly what happens on a cosmic scale. The universe doesn't have a center from which everything is flying away. Every point in the cosmos sees all other distant points moving away, and every observer, no matter where they are, will measure the same kind of large-scale expansion. This means that if you could somehow stand in a galaxy 10 billion light-years away, you'd see the Milky Way rushing away from you just as we see that galaxy receding from us. It's a truly mind-bending concept, a universe that stretches everywhere all at once. This expansion only affects the vast cosmic distances, not the local scales we live on. Gravity holds galaxies, solar systems, and even atoms tightly enough that they don't expand with the universe. The Earth isn't getting farther from the sun. Your coffee cup isn't stretching. The forces holding these things together are far stronger than the gentle cosmic stretching of space. Expansion only becomes noticeable when we look across the immense voids between galaxies, distances of millions or billions of light years. But how exactly do scientists know this? If space is stretching, shouldn't it leave some kind of measurable sign? Indeed it does, in the form of light. When light travels through the universe, it rides along the expanding fabric of space. As that space stretches, so too does the wavelength of the light itself. What was once blue or white light gets pulled toward the red end of the spectrum, a phenomenon known as redshift. This redshift is one of the most powerful pieces of evidence we have that space is expanding, and it's what first led astronomers to the astonishing realization that the universe is not static at all. But before we jump ahead to how that discovery happened, let's pause for a moment to appreciate how revolutionary this idea truly is. The concept that space itself can stretch defies everyday experience. In our daily lives, we see motion through space, cars moving down a road, planets orbiting the sun. But the motion of space itself, that's something entirely different. It's as though the rules of reality stretch and reshape themselves at the largest scales. According to general relativity, Einstein's great theory of gravity, space and time form a single, dynamic entity, space-time. It's not just an empty stage on which matter acts, it's an actor itself, capable of bending, curving, and evolving. When we say the universe expands, we're describing how space-time itself changes, how the geometry of the cosmos evolves over time. Every cubic centimeter of the universe is slowly stretching, and because there's so much of it, the effect becomes enormous when measured across billions of light years. This cosmic expansion has been happening for roughly 13.8 billion years, ever since the universe emerged from its primordial beginning, what we now call the Big Bang. In those earliest moments, space expanded at a staggering rate, carrying energy and matter outward as the cosmos grew from an unimaginably hot, dense state into the vast expanse we observe today. That process has never stopped. It's just slowed down and changed character as the universe evolved, leading to the vast, structured cosmos we see in the night sky. So when cosmologists say the universe is expanding, they don't mean that galaxies are shooting through space like rockets. They mean that the distance between galaxies grows because space itself is stretching. The universe isn't expanding into anything, nor does it have an edge. It's space itself, the very fabric of existence, that's changing. The cosmic stage isn't fixed. It's breathing, stretching, and evolving. And while that idea may sound abstract, its discovery was rooted in something beautifully concrete: the light from distant galaxies. In the early 20th century, one astronomer looked deep into the cosmos and found patterns that no one had ever seen before. Patterns that changed everything we thought we knew about the universe. His name was Edwin Hubble, and what he found would rewrite the story of the cosmos forever. The story of how humanity first discovered that the universe is expanding begins in the 1920s, an era when our understanding of the cosmos was undergoing a revolution. Before that decade, most astronomers believed that the Milky Way was the entirety of the universe, that the stars, nebulae, and faint smudges visible in the night sky all belonged to a single, enormous galactic system. The idea of countless other galaxies existing beyond our own was not yet widely accepted. But a young American astronomer named Edwin Hubble, working at the Mount Wilson Observatory in California, was about to change that forever. Using the world's most powerful telescope at the time, the 100-inch Hooker telescope, Hubble began studying faint, cloud-like patches of light known as spiral nebulae. Many astronomers believed these were just gas clouds within our galaxy, but Hubble's meticulous observations suggested otherwise. By identifying special types of variable stars called Cepheid variables within these nebulae, he was able to estimate their distances. What he found was astonishing. These nebulae were far too distant to be part of the Milky Way. They were entire galaxies, island universes, scattered throughout an unimaginably vast cosmos. This discovery alone was monumental. It expanded humanity's view of the universe from one galaxy to billions. But Hubble's most groundbreaking revelation was still to come. As he measured the light from these galaxies, he noticed something peculiar. Their light was shifted toward the red end of the spectrum. This red shift meant that the light waves had been stretched, as if the galaxies were moving away from us, causing their emitted light to stretch out as they receded. At first, Hubble thought this might be a coincidence or a local effect. But the more galaxies he measured, the clearer the pattern became. He plotted their velocities, how fast they were moving away from us, against their distances, and what emerged was a striking straight-line relationship. The farther away a galaxy was, the faster it seemed to be moving away from us. This relationship would come to be known as Hubble's law, and it became the first direct evidence that the universe itself is expanding. The discovery was both elegant and shocking. It suggested that the cosmos was not static, as many had long assumed, but dynamic and changing, expanding like a growing balloon. Every galaxy was moving away from every other galaxy, not because they were flying through space, but because the fabric of space itself was stretching. In one stroke, Hubble had provided observational proof of what Albert Einstein's general theory of relativity had already hinted at, that the universe could expand or contract, depending on its energy and matter content. Einstein himself was deeply surprised by Hubble's results. When he first developed general relativity in 1915, his equations predicted a universe that could not remain static. It had to either expand or collapse. But at the time, the scientific consensus was that the universe was eternal and unchanging, so Einstein added a cosmological constant, a mathematical fudge factor, to counteract the pull of gravity and keep the universe stable. When Hubble's observations showed that the universe was actually expanding, Einstein reportedly called his earlier modification the biggest blunder of my life. Hubble's discovery didn't just confirm that the universe was expanding, it also provided a way to measure that expansion.
The slope of the line in Hubble's law, known as the Hubble constant, represents the rate at which galaxies recede per unit of distance. Although astronomers have refined this value many times over the past century, its basic meaning remains the same. It quantifies how quickly the universe is growing today. The implications were staggering. If galaxies are moving apart now, then logically, in the past, they must have been closer together. Follow that reasoning backward and you reach a moment when everything, all matter, energy, and space itself, was concentrated in a single, incredibly dense point. This realization would eventually give rise to one of the most profound theories in all of science, the Big Bang. But at the time, Hubble's discovery raised more questions than it answered. Was the expansion uniform everywhere? Would it continue forever, or would gravity eventually slow it down? And perhaps most intriguingly, if all galaxies are receding, what does that say about our own place in the universe? Are we at the center of it all? The answer, as it turns out, is no. The expansion of the universe looks the same from every vantage point. Just as any dot on an inflating balloon sees all other dots moving away, every galaxy observes the same cosmic pattern. There is no central point of expansion, no privileged location in the universe. The cosmos doesn't expand from somewhere, it expands everywhere. Hubble's 1920s observations transformed cosmology from philosophy into a quantitative science. The universe was no longer a static, eternal stage. It was a living, evolving entity with a history and potentially a future. The idea that space itself was stretching gave rise to entirely new questions about the fate of the cosmos, the origin of matter and energy, and the very nature of reality. And yet, as revolutionary as Hubble's findings were, they depended on one subtle clue hidden in the starlight itself, a clue that allowed astronomers to measure motion across billions of light years. That clue is known as redshift, and it would become the Rosetta Stone for understanding the universe's expansion.
When Edwin Hubble and his colleagues began to examine the faint light of distant galaxies, they weren't just looking at pretty smudges through a telescope. They were reading a cosmic message written in light itself. Every beam of light that reaches Earth carries within it a signature of its origin, information about the temperature, composition, and motion of its source. And among those signatures lies one of the most powerful clues in cosmology, redshift. To understand redshift, we first have to grasp a simple but profound idea. Light behaves like a wave. Just as sound waves can stretch or compress depending on how the source moves, light waves do the same when their source moves relative to an observer. This is known as the Doppler effect, a phenomenon most people experience every day without realizing it. When an ambulance passes by with its siren blaring, the pitch sounds higher as it approaches and lower as it moves away. That's because the sound waves are compressed in front of the moving vehicle and stretched behind it. Now imagine that same concept applied to light on a cosmic scale. When a galaxy moves toward us, the light waves it emits are slightly compressed, shifting toward the blue end of the spectrum. We call this a blue shift. But when a galaxy moves away, its light waves are stretched out, shifting toward the red end of the spectrum, a red shift. This stretching of light is subtle, but measurable. By comparing the pattern of spectral lines, the unique fingerprints of elements like hydrogen and helium, astronomers can tell exactly how much the light has shifted. The greater the red shift, the faster the object is receding from us. When Hubble first plotted those measurements against the distances to galaxies, he found that nearly every galaxy showed a redshift, meaning almost all of them were moving away. And not just moving away, but doing so in a systematic pattern. The farther away a galaxy is, the faster it recedes. This discovery was monumental. It meant the redshift wasn't caused by galaxies moving through space like projectiles. It was caused by the expansion of space itself, stretching the light as it traveled. Every photon emitted by a distant galaxy must cross billions of light years of expanding space before reaching us. During that journey, space itself stretches, pulling the light wave with it. By the time it arrives, the wavelength has been elongated, shifted toward the red. The importance of this cannot be overstated. Redshift is not just a measure of motion, it's a measure of cosmic history. When we detect a redshift of a galaxy, we're not simply seeing where it is now,
we're seeing where it was billions of years ago when the light first began its journey. The farther away a galaxy is, the older the light we're seeing, and the greater its redshift. In this way, redshift functions like a time machine, allowing astronomers to peer back through the epochs of cosmic evolution. But there's an even deeper layer to what redshift reveals. It tells us that the universe itself is dynamic, that the very geometry of reality changes with time. In an expanding universe, light traveling through space gets stretched not because of motion through space, but because of the changing scale of space itself. This phenomenon is known as cosmological redshift, and it's fundamentally different from the ordinary Doppler effect. It's not that galaxies are flying away into pre-existing emptiness. It's that space itself is stretching, carrying galaxies along like boats drifting apart on a rising tide. Cosmological redshift also provides one of the strongest observational foundations for the Big Bang theory. When scientists extrapolate the observed expansion backward in time, it implies that the universe was once smaller, denser, and hotter. The redshift we see in distant galaxies is essentially a fossil imprint of that ongoing expansion, a continuous echo of the universe's birth. Beyond its role in revealing expansion, redshift has become one of the most critical tools in modern astronomy. By measuring redshifts, scientists can determine not only how fast objects are receding, but also how far away they are. Large-scale redshift surveys have mapped the three-dimensional structure of the universe, showing that galaxies are not scattered randomly, but form a vast cosmic web. Enormous filaments, clusters, and voids that stretch across billions of light years. Redshift also allows astronomers to measure the universe's expansion rate expressed through the Hubble constant. By comparing redshift data with independent distance measurements, scientists can estimate how quickly the universe is expanding today. In this way, every faint photon captured by a telescope becomes part of a grand equation, one that tells the story of how the universe evolves, how it began, and perhaps how it will end. But redshift's importance doesn't stop with galaxies. It's also woven into the light that fills the cosmos itself, the faint afterglow of the Big Bang, known as the cosmic microwave background. This radiation has been redshifted over billions of years from searing ultraviolet and X-ray energies down to the cool microwave frequencies we detect today. That shift tells us just how much the universe has expanded since its fiery beginning, roughly 1,000-fold. In short, redshift is the universe's language of motion and time. It is the key that unlocked the realization that we live in an expanding cosmos, and it continues to be the fundamental tool for measuring that expansion. Through redshift, we've learned that galaxies are not static beacons frozen in the night, but ancient travelers drifting away on an ever-stretching sea of space-time. And yet, behind this discovery lay a theoretical framework that made sense of it all, the mathematics of Einstein's general relativity. It was Einstein's equations that first predicted a universe that could expand or contract. But at the time, even Einstein couldn't bring himself to believe it. In his quest to make the universe static, he introduced something he later regretted deeply: the cosmological constant. When Albert Einstein unveiled his general theory of relativity in 1915, he didn't just change physics, he changed our understanding of reality itself. For the first time, gravity was no longer a mysterious force acting at a distance, as Isaac Newton had described. Instead, Einstein revealed that what we perceive as gravity is the curvature of space-time, the bending of the very fabric of the universe by mass and energy. Massive objects like stars and planets distort space-time around them, and smaller bodies simply follow the curves and contours of that distortion. It was a breathtakingly elegant idea, one that unified space, time, and gravity into a single geometric framework. But Einstein's new theory didn't stop there. When he applied his equations to the universe as a whole, to all of space, time, and matter, he stumbled upon a shocking implication. The universe couldn't remain static. His mathematics demanded that space must either be expanding or contracting. There was no equilibrium point, no perfectly balanced eternal cosmos. The equations insisted that the universe was dynamic, evolving, and in motion.
This result deeply troubled Einstein. At the time, around 1917, the scientific and philosophical consensus was that the universe was eternal and unchanging. The night sky appeared stable. Galaxies, or what were then thought to be nebulae, didn't seem to move in any dramatic way. The very idea of an expanding or contracting cosmos sounded absurd. So faced with equations that contradicted what everyone, including himself, believed, Einstein made a fateful decision. He modified his equations. To counteract the gravitational pull that would cause the universe to collapse under its own mass, Einstein introduced an extra term, a kind of anti-gravity factor, which he called the cosmological constant, represented by the Greek letter lambda. This constant provided a repulsive force that perfectly balanced gravity on cosmic scales, keeping the universe static and stable. In essence, Einstein fine-tuned the universe mathematically to prevent it from changing. His cosmological constant acted as a form of energy inherent to empty space itself, a uniform pressure pushing outward everywhere, strong enough to resist gravitational collapse. The idea allowed him to preserve the philosophical comfort of a timeless, unchanging cosmos, a universe that simply is, rather than one that evolves. But history would prove that nature had no interest in philosophical comfort. In 1929, Edwin Hubble's groundbreaking observations showed that distant galaxies were receding from us, their light redshifted in a pattern consistent with the universe that was expanding. This discovery directly contradicted the static universe Einstein had worked so hard to preserve. Suddenly, the extra term he had added, the cosmological constant, wasn't necessary at all. Gravity and motion alone could account for the universe's behavior, without any artificial balancing force. When Albert Einstein learned of Hubble's findings, he reportedly lamented that his introduction of the cosmological constant was the biggest blunder of my life. Although historians debate the exact phrasing, the sentiment rings true. Einstein realized that his attempt to force the universe into a static state had blinded him to one of his own theory's most profound predictions, the natural expansion of the cosmos. Ironically, the cosmological constant that Einstein dismissed would make a triumphant return decades later, under a new name: dark energy. But during Einstein's lifetime, the discovery of the expanding universe marked a turning point. It meant that the cosmos had a history, a beginning, and that its future would depend on the balance between gravity and expansion. Einstein's equations, even without the cosmological constant, became the foundation of modern cosmology. They describe how the geometry of space-time evolves under the influence of energy and matter, giving rise to what we now call the Friedmann-Lemaitre-Robertson-Walker model, a mathematical description of an expanding universe that fits perfectly with observation. What's especially fascinating is that Einstein's theory didn't just allow for expansion, it demanded it. Once you take general relativity seriously and apply it to the entire cosmos, you find that a static universe is unstable. A tiny nudge in either direction, a little more density, a little less, would cause space to either collapse inward or swell outward. The cosmic balance Einstein tried to create was like a pencil standing on its tip, mathematically possible, but physically impossible to sustain. And yet, within Einstein's blunder was hidden a deeper truth. The cosmological constant represented a kind of energy of empty space itself, a repulsive pressure built into the fabric of space-time. Although Einstein discarded it, modern physicists have resurrected the idea to explain why the universe's expansion is accelerating today. In a way, Einstein's mistake was not in inventing the cosmological constant, but in giving up on it too soon.
His equations, stripped of the constant, laid the groundwork for what would soon become the most famous cosmological model of all time, the Big Bang Theory. The notion that the universe is expanding naturally leads to one stunning conclusion. If it's growing larger with time, then at some point in the distant past, it must have been smaller, denser, and unimaginably hot. This insight would change not only cosmology, but our entire understanding of existence itself. The expansion that Einstein's equations predicted, that Hubble's telescope confirmed, and that redshift revealed to our eyes all pointed toward a singular cosmic beginning, an origin of space and time. And that brings us to the next great step in this journey, the birth of the Big Bang model, the story of how everything, from galaxies to atoms to life itself, emerged from a single blazing moment of creation. The realization that the universe was expanding led to one of the most profound and transformative ideas in all of human thought, that everything we see today, every galaxy, star, planet, and atom, once emerged from a single incredibly dense and unimaginably hot beginning. This idea, which we now call the Big Bang, did not come from a single moment of inspiration, but from decades of careful reasoning and observation that gradually rewrote our understanding of reality itself. When Edwin Hubble's observations in the late 1920s revealed that galaxies were moving away from one another, the logical conclusion was unavoidable. If everything is spreading apart now, then at some earlier time, everything must have been much closer together. Push this expansion backward far enough, and the distances between all things shrink to zero. Not just the space between galaxies, but space itself. The universe, it seemed, must have once been concentrated into a single unified state, a point of infinite density and temperature where the known laws of physics break down. This wasn't merely a philosophical idea. It was a physical reality suggested by the mathematics of general relativity. The concept was first explored seriously by a Belgian priest and astrophysicist named Georges Lemaitre in the 1920s. He proposed that the universe began as what he called a primeval atom, an initial cosmic seed containing all the matter and energy that would later form everything in existence. According to Lemaitre, this dense beginning exploded outward, setting space and time into motion and initiating the expansion we still observe today. At first, many scientists resisted the idea. Even Einstein himself dismissed it, calling it inspired but unsatisfactory. But over time, evidence began to mount. The equations of general relativity, when solved under realistic cosmic conditions, consistently pointed toward a dynamic universe that expanded from an initial singularity. Russian mathematician Alexander Friedman had shown as early as 1922 that an expanding or contracting universe was not only possible, but required by Einstein's own theory. Lemaitre and Friedman's work together laid the theoretical groundwork for the Big Bang concept long before the term itself existed. The phrase Big Bang wouldn't be coined until 1949, and interestingly, it was meant as an insult. British astronomer Fred Hoyle, who championed a competing idea known as the steady-state model, used the term mockingly during a radio broadcast. Hoyle argued that the universe had no beginning or end, that new matter was constantly being created to keep the overall density of the universe constant as it expanded. But ironically, the catchy phrase he intended as derision became the enduring name of the very theory that would eventually prove him wrong. So what exactly does the Big Bang model say? It tells us that the universe began roughly 13.8 billion years ago from an extremely hot, dense, and compact state. At that moment, the origin of space and time, all energy, matter, and the fundamental forces were united in a single, undifferentiated form. There was no before because time itself began with the Big Bang. The universe didn't explode into space, it was space itself that expanded, carrying energy outward in every direction. In its earliest instance, the universe was so dense that ordinary matter couldn't even exist. Instead, it was a seething plasma of pure energy, quarks, and photons. Within a tiny fraction of a second, a period known as cosmic inflation is believed to have occurred. A brief but stupendous burst of expansion that stretched the universe exponentially. In less than a heartbeat, regions smaller than a proton ballooned to cosmic scales. This inflationary epoch smoothed out the universe and set the stage for the structures that would later form. As the universe continued to expand, it began to cool.
Quarks combined to form protons and neutrons, which in turn fused into the first atomic nuclei, mostly hydrogen and helium, within the first few minutes. This process, known as primordial nucleosynthesis, left behind the elemental foundation for everything that would later exist. For the next several 100,000 years, the universe remained a glowing fog of charged particles and radiation. Light couldn't travel freely because it was constantly scattered by matter. Then, about 380,000 years after the Big Bang, a remarkable transition occurred. The universe cooled enough for electrons to combine with nuclei, forming the first neutral atoms. With that, light was finally able to move unimpeded through space. That ancient light, the cosmic microwave background radiation, still fills the universe today, stretched and cooled by billions of years of expansion. It is quite literally the afterglow of creation, a snapshot of the universe when it was just a baby. This relic radiation became the smoking gun for the Big Bang Theory. When it was discovered by accident in 1965 by Arno Penzias and Robert Wilson, it provided the evidence that scientists had long sought, proof that the universe had indeed begun in a hot, dense state and had been expanding and cooling ever since. The steady-state model couldn't account for such a pervasive background glow. Only the Big Bang could. From that point on, the Big Bang Theory became the cornerstone of modern cosmology. It explains not just the expansion of the universe, but the abundance of light elements, the distribution of galaxies, and the structure of the cosmic web itself. The more precisely we observe the universe through telescopes like Hubble and more recently the James Webb Telescope, the more deeply the evidence aligns with this picture of an evolving, expanding cosmos that began in fire and continues to unfold in silence.
Yet the Big Bang is not the end of the story, it's only the beginning. After that primordial expansion, the universe entered a new era, one defined by the slow tug-of-war between gravity and the momentum of expansion. Matter began to clump together, forming stars, galaxies, and clusters. Cosmic history unfolded as a grand interplay between attraction and expansion, a delicate balance that would shape everything we see today. And so, from the searing birth of space and time itself, the universe began its long journey toward the present day, cooling, expanding, and evolving over billions of years. What happened next, how matter organized itself into the cosmic structures we know, and how gravity fought against expansion, is the next step in understanding not just how the universe began, but how it became what it is now. After the first brilliant burst of creation, the universe entered a long and complex process of transformation. The Big Bang was not a conventional explosion in space. It was the birth of space itself, expanding and cooling as time unfolded. In the beginning, the cosmos was filled with searing energy and fundamental particles, a roiling sea of light and matter indistinguishable in the chaos of unimaginable temperatures. But from that primordial fire, order slowly began to emerge. The universe's story is, in essence, the story of how simplicity evolved into complexity, how pure energy gave rise to matter, how matter assembled into stars and galaxies, and how those galaxies became the cosmic scaffolding of everything we see today. In the first fraction of a second, the universe was a storm of fundamental forces and particles. The laws of physics as we know them were still separating out from an initial state of unity. Gravity, electromagnetism, and the strong and weak nuclear forces began to take distinct forms. During this fleeting instant, less than 10 to the negative 36 seconds after the Big Bang, the universe underwent what physicists call cosmic inflation, an inconceivably rapid expansion that caused it to grow exponentially in size in an instant. Regions that were once subatomic in scale ballooned to macroscopic proportions in an instant, smoothing out any irregularities and ensuring the near uniformity of the universe we observe today. After inflation slowed, the energy driving it transformed into a dense bath of particles and radiation. The universe was still only microseconds old, but the seeds of everything to come had already been sown. Quarks, the building blocks of protons and neutrons, darted through a thick plasma of photons, electrons, and neutrinos. As the universe expanded, it cooled, and cooling allowed new forms of matter to emerge. By the time the cosmos was a mere 1 second old, the temperature had dropped enough for protons and neutrons to form from quarks. Within minutes, these protons and neutrons fused into the first atomic nuclei, mostly hydrogen, helium, and trace amounts of lithium. This epoch, called primordial nucleosynthesis, created the basic chemical ingredients that still dominate the universe today. For the next 380,000 years, the universe remained a brilliant fog of charged particles and light. Photons, particles of light, could not travel freely, constantly scattering off electrons in a dense plasma. The cosmos glowed like the surface of a star, opaque and filled with energy. During this era, tiny fluctuations in density, slight differences in how matter was distributed, began to grow under the influence of gravity. These fluctuations were incredibly small, perhaps only 1 in 100,000. But over billions of years, they would become the foundation for galaxies and clusters. Then came one of the most significant transitions in the history of the universe: recombination. Around 380,000 years after the Big Bang, the universe had cooled to about 3,000 Kelvin, cooling enough for electrons to combine with protons and form neutral hydrogen atoms. This epoch suddenly made the universe transparent to light, allowing photons to stream freely through space for the first time. The afterglow of this moment still surrounds us today as the cosmic microwave background radiation, CMB, a faint, omnipresent echo of the universe's birth. The CMB is like a photograph of the cosmos as it was in its infancy, a map of those first fluctuations that would later grow into galaxies. After recombination, the universe entered what astronomers call the cosmic dark ages. The light from the Big Bang continued to fade and stretch as space expanded, and no new sources of light yet existed. During this time, gravity quietly went to work. It began to pull together slightly denser regions of matter, amplifying their growth while the surrounding space continued to thin out. Over millions of years, these dense pockets became the first cosmic structures, enormous clouds of hydrogen and helium gas slowly collapsing under their own weight. Roughly 100 to 200 million years after the Big Bang, the darkness was finally broken. In these collapsing clouds, the pressure and temperature became so intense that hydrogen atoms began to fuse into helium. The first stars were born, titanic, short-lived giants that burned hot and bright, flooding the young universe with ultraviolet radiation. These early stars, known as population 3 stars, were unlike any that exist today, composed almost entirely of hydrogen and helium. They lived fast and died violently, exploding as supernovae that enriched the surrounding gas with heavier elements, the raw materials for planets, moons, and eventually life. As these stars formed in groups, their mutual gravity pulled them into larger and larger systems. Over hundreds of millions of years, those clusters of stars became the first galaxies, immense rotating islands of light. The universe entered an age of structure formation. While the cosmic expansion continued on vast scales, gravity worked locally to create order out of chaos. Where matter was concentrated enough, gravity overpowered the general expansion, binding regions of space together. These gravitationally bound systems became galaxies, and galaxies in turn grouped into clusters and filaments, forming a vast cosmic web that stretched across billions of light years. By about 1 billion years after the Big Bang, the universe had transformed from a nearly featureless fog into a rich, structured cosmos filled with galaxies and glowing stars. The ultraviolet radiation from those first generations of stars and galaxies reionized the remaining intergalactic gas, ending the dark ages completely. From that point forward, the universe was illuminated, not by the fading light of the Big Bang, but by the countless suns born within it.
Over the next billions of years, new generations of stars continue to form, die, and recycle their material back into space. Supernovae spread heavy elements like carbon, oxygen, iron, and silicon, the ingredients for rocky planets and organic chemistry. Galaxies merged and evolved, sometimes colliding in titanic cosmic dances that reshape their structure. Out of these vast processes, our own Milky Way galaxy took shape, and within it, roughly 9 billion years after the Big Bang, our solar system emerged from a swirling cloud of dust and gas. Throughout all of this, the expansion of the universe never stopped. Space continued to stretch, increasing the distances between galaxies not gravitationally bound to one another. Locally, gravity built complex structures, stars, planets, galaxies, but on the grandest scales, expansion carried everything apart. The universe was a balance between two opposing tendencies: the pull of gravity, which sought to bring matter together, and the momentum of expansion, which drove everything apart. For billions of years, it seemed that gravity might eventually slow the expansion, perhaps even reverse it in some distant future. But as astronomers would later discover, something extraordinary was happening instead. The universe's expansion was not slowing down at all. It was accelerating, pushed faster and faster by a mysterious force that no one had expected. That revelation would come much later, in the twilight of the 20th century, when scientists studying distant supernovae found that the universe's growth was speeding up, a finding so astonishing that it would shake cosmology to its core and revive, in a stunning twist of fate, Einstein's long-abandoned cosmological constant. By the late 20th century, astronomers believed they had a fairly clear picture of how the universe worked. The Big Bang theory had long since replaced older ideas like the steady-state model, and observations across the electromagnetic spectrum confirmed that the cosmos was expanding, just as Hubble had discovered decades earlier. The lingering question wasn't whether the universe was expanding, but how that expansion was changing over time. For decades, most scientists assumed that the rate of expansion must be slowing down. After all, gravity, the universal force of attraction, works to pull matter together. Even though the universe was expanding, its enormous mass should gradually be tugging everything back, slowing the cosmic stretching. Astronomers debated whether this deceleration would be strong enough to eventually halt the expansion and cause the universe to collapse back into Big Crunch, or whether it would continue expanding forever, just at an ever-diminishing pace. To settle the matter, scientists needed a way to measure how the expansion rate had changed over cosmic history. The challenge was that the universe doesn't come with a built-in clock or ruler. To trace its expansion across time, astronomers would need standard candles, celestial objects whose true brightness could be known with precision. By comparing their known intrinsic luminosity to how bright they appear from Earth, astronomers could calculate their distance. Combine that with redshift measurements, and you could reconstruct how fast the universe was expanding at different points in its past. The ideal candidate for this work turned out to be a particular kind of exploding star known as Type A supernovae. These cataclysmic events occur in binary systems, where a white dwarf star, the dense remnant of a dead star, steals material from a companion until it reaches a critical mass and detonates in a thermonuclear explosion. Because all Type A supernovae explode under roughly the same conditions, they reach almost identical peak brightness. This consistency makes them extraordinarily valuable as cosmic distance markers, cosmic beacons that shine briefly but reveal enormous truths. In the 1990s, two independent teams of astronomers set out to use these stellar explosions to chart the history of cosmic expansion. One group, the Supernova Cosmology Project, was led by Saul Perlmutter at Lawrence Berkeley National Laboratory. The other, the High-Z Supernova Search Team, was co-led by Brian Schmidt and Adam Rees. Both teams worked tirelessly to identify and measure distant supernovae billions of light years away whose light had been traveling through space since the early epochs of the universe. Their goal was simple but profound: determine whether the expansion of the universe was slowing down, and if so, by how much. Yet what they found defied every expectation. When the data came in, the supernovae appeared dimmer than they should have been, not because of dust or error, but because they were farther away than expected in a decelerating universe. This could only mean one thing: the expansion of the universe had actually been speeding up. The implications were staggering. Instead of slowing under the pull of gravity, the universe's expansion was accelerating, as if some mysterious force was pushing galaxies apart faster and faster over time. This discovery, first announced in 1998, sent shockwaves through the scientific community.
The results were so unexpected that both teams double and triple checked their data, searching for any alternative explanation. But the evidence held firm. The universe wasn't coasting or collapsing, it was running away from itself. This revelation was nothing short of revolutionary. It implied that some previously unknown component of the cosmos was at work, a kind of repulsive energy embedded in the fabric of space itself that counteracted gravity on the largest scales. To account for this acceleration, scientists revived an idea that had been discarded for decades: Einstein's cosmological constant, the term he once introduced to make the universe static and later called his biggest blunder. Perhaps they realized it hadn't been a blunder after all.
The discovery of cosmic acceleration completely reshaped modern cosmology. It revealed that everything humanity had thought about the universe's fate was incomplete. The cosmos wasn't slowing down towards stillness, it was racing ahead, driven by a hidden force that seemed to grow stronger as space expanded. This mysterious phenomenon would soon be given a name: dark energy. In 2011, the Nobel Prize in Physics was awarded to Saul Perlmutter, Brian Schmidt, and Adam Rees for their pioneering work uncovering this astonishing truth. Their findings opened an entirely new chapter in cosmology, one filled with more questions than answers. What exactly was causing the acceleration? Why did it start dominating the universe only a few billion years ago? And what does it mean for the ultimate fate of everything that exists? The late 1990s thus marked the dawn of a new cosmic mystery. Humanity had discovered not just that the universe was expanding, but that it was expanding faster and faster, as though pushed by an invisible hand. The more the universe stretched, the more this mysterious force seemed to take control, leaving scientists to grapple with the unsettling realization that most of the cosmos was made of something entirely unknown. This discovery would lead directly to the next great question in our story. Why is the universe's expansion accelerating? What is this hidden energy that fills all of space and drives galaxies apart? In searching for that answer, scientists would confront one of the deepest enigmas in all of physics: the nature of dark energy. When astronomers first realized that the universe's expansion was accelerating, the scientific world was stunned. It wasn't merely unexpected, it was profoundly counterintuitive. For nearly a century, ever since Einstein's general relativity and Hubble's discovery of cosmic expansion, scientists had assumed that gravity, the great cosmic attractor, must be working tirelessly to slow the expansion down. Every galaxy, every cluster, every atom of matter in the universe exerts a gravitational pull on every other. So logically, even though the universe was expanding, that expansion should have been fighting against gravity's endless tug. It was such a reasonable expectation that almost no one seriously questioned it. Whether one believed the universe would expand forever or eventually collapse, everyone assumed that gravity would at least be putting up resistance. The only real debate was how strong that resistance would be and whether it would eventually win. In simple terms, scientists expected the universe to behave a bit like a ball tossed into the air. The Big Bang was the throw, a burst of energy propelling space outward. Gravity in this analogy was like Earth's pull, gradually slowing the ball's climb. The only question was, would the ball eventually fall back, a closed universe, coast to a stop, a flat universe, or keep rising forever at a diminishing speed? But the observations from the late 1990s didn't fit any of these expectations. When astronomers studied the light from distant Type A supernovae, they found that the universe wasn't like a ball slowing down. It was like a ball that had started speeding up again after the throw, as if some unseen force were giving it an extra push. That discovery upended then nearly everything cosmologists thought they understood about cosmic evolution. This wasn't just a small adjustment to existing theories. It was a seismic shift in the foundations of physics. The discovery meant that gravity wasn't the only large-scale force shaping the fate of the cosmos. Something else was at play. Something that didn't behave like matter, that didn't clump together under gravity, and that seemed to have the exact opposite effect. Rather than pulling things together, it was pushing them apart.
This was, in every sense, one of the most shocking revelations in modern science. The entire 20th century had been built on the triumph of understanding gravity, from Newton's laws to Einstein's relativity. Yet now, the universe itself seemed to be telling us that our understanding was incomplete. Something in the cosmic equations wasn't adding up. What made the discovery even more unsettling was when this acceleration seemed to have begun. Observations showed that for the first several billion years after the Big Bang, the universe's expansion did indeed slow down, as expected. Gravity dominated then. Matter was dense enough to exert a strong pull. But as the universe continued to expand and matter spread out, that gravitational pull weakened. At some point, roughly 5 to 6 billion years ago, the balance shifted. Instead of slowing down, the expansion began to speed up. This abrupt change suggested that whatever was driving the acceleration had always been present, quietly lurking in the background, but had only become dominant once the universe had grown large enough and matter had become sufficiently diffuse. It was as if a hidden force had been waiting patiently for its moment to take over. And now, in the latter half of the universe's history, it had seized control of cosmic destiny. The implications were vast. For one, this mysterious force seemed to make up a huge fraction of the universe's total energy. If it was driving cosmic expansion on the largest scales, then it had to be everywhere, not in galaxies or stars, but in the very fabric of space itself. And yet, no one could detect it directly. It wasn't made of particles, it didn't emit light, and it couldn't be measured with traditional instruments. Scientists were faced with an almost philosophical question dressed as a physical one. What is the universe made of? Because if this new repulsive energy was real, it meant that everything we could see, the galaxies, stars, planets, and all known matter, was only a small fraction of the total cosmic inventory. The rest was something invisible, inscrutable, and pervasive. The reaction across the scientific community was a mix of disbelief and wonder. Some researchers initially suspected observational errors, perhaps dust or calibration mistakes, had made the supernovae appear dimmer and farther than they truly were. But as more data poured in from different telescopes and independent teams, the pattern was undeniable. The acceleration was real. It's difficult to overstate how profoundly this discovery changed cosmology. Before 1998, cosmologists believed they were closing in on a final model of the universe. Afterward, they realized that most of the universe was made up of something they didn't understand at all. It was as if explorers, after mapping their entire world, suddenly discovered that the map covered only a small island, and that the ocean beyond was vast and uncharted. Gravity, once thought to be the undisputed ruler of cosmic fate, had been challenged by a mysterious new force that no one had ever seen. This realization forced scientists to rethink the nature of space itself. Could it be that empty space wasn't truly empty, but filled with an energy that exerts pressure, not attractive like gravity, but repulsive? To explain the accelerating expansion, physicists revived an old idea, one that Einstein himself had once discarded. They called it dark energy, an unseen component of the cosmos that acts as a kind of anti-gravity. Dark energy became the leading candidate to explain why the universe continues to expand at an ever faster rate. But naming it didn't solve the mystery, it only deepened it. What is dark energy really? Is it Einstein's cosmological constant resurrected, a fixed property of space? Or could it be something dynamic, a new kind of energy field evolving over time? Whatever it is, it represents perhaps the greatest enigma in modern science, one that continues to challenge our understanding of reality itself. When the realization of the universe's accelerating expansion finally sunk in, scientists found themselves staring at one of the most profound mysteries ever encountered. Something was working against gravity. Something invisible, omnipresent, and astonishingly powerful was driving galaxies apart, faster and faster, across the cosmic void. And yet,
no one could see it. No one could detect it directly. To describe this unknown force, astronomers reached for a simple but evocative term: dark energy. The name itself reflects both our understanding and our ignorance. It is energy because, whatever it is, it acts like a property of space that has real, measurable effects on the universe's dynamics. And it is dark because we do not know its nature. It emits no light, it interacts weakly, if at all, with matter, and it remains beyond the reach of our instruments. But its fingerprints are unmistakable. The accelerated expansion of the universe is the signature of something profound and pervasive, and dark energy is the best label we have for it. The concept of dark energy wasn't conjured out of nowhere. In fact, it can be seen as a modern resurrection of Einstein's cosmological constant, that term he added to his equations of general relativity to balance gravity and keep the universe static. Einstein may have discarded it as a mistake, but decades later, cosmologists realized that something very much like it might actually exist, not as a mistake, but as a fundamental feature of the cosmos. According to Einstein's theory, the energy of space itself has gravitational effects. Normally, gravity is attractive. Mass pulls mass together. But a uniform energy inherent to space, a vacuum energy, behaves differently. Rather than drawing matter in, it pushes it apart. The greater the amount of space there is, the more of this energy there is, and therefore the stronger the repulsive effect becomes as the universe expands. In other words, the expansion of space feeds on itself. This idea fit beautifully and eerily with the observations from the late 1990s. The data from Type A supernovae showed that the universe's expansion wasn't slowing, but accelerating, as though driven by a constant pressure pushing outward from every direction. It was as if the vacuum of space had weight, or rather anti-weight, a built-in ability to stretch the cosmos faster over time. The simplest way to describe this phenomenon mathematically was to reintroduce Einstein's cosmological constant as a form of dark energy that filled all of space uniformly. But calling it simple is deceptive. The implications were staggering. If dark energy truly exists, it doesn't just nudge the universe, it dominates it. To drive the expansion on such immense scales, dark energy would have to account for nearly 70% of the total energy content of the universe. Everything else, all the galaxies, stars, planets, and all known matter, would make up only a third of the total cosmic inventory. The cosmos, it seemed, was not made primarily of matter, but of emptiness charged with an invisible, repulsive energy. Dark energy acts as a cosmic pressure, countering gravity's pull and stretching the fabric of space itself. But unlike ordinary matter or radiation, its density doesn't dilute as the universe expands. When galaxies move apart, their matter density decreases because the same amount of mass is spread over a larger volume. But dark energy behaves differently. Its density remains roughly constant, meaning that as the universe grows, more and more dark energy comes into play. The result is a kind of runaway effect. The bigger the universe gets, the faster it expands. This bizarre behavior is unlike anything else in physics. It doesn't fit comfortably within our existing models of particles or forces. Some scientists interpret dark energy as a cosmological constant, an intrinsic property of space that has always existed and will never change. Others believe it might be something more dynamic, a new kind of energy field evolving over cosmic time. Still others suggest it could arise from modifications to Einstein's equations themselves, implying that gravity behaves differently on cosmic scales than we currently understand. But whatever its true nature, dark energy represents a monumental shift in our cosmic worldview. Before its discovery, scientists thought they were close to understanding the universe's major components: ordinary matter, dark matter, and radiation. Afterward, they realized that the dominant force shaping the cosmos was something entirely unknown, an energy that doesn't clump, can't be seen, and yet determines the ultimate fate of everything. In many ways, the introduction of dark energy parallels the early history of gravity itself. When Newton first proposed the law of universal gravitation, he couldn't explain how gravity worked, only that it did. Likewise, today's cosmologists can describe dark energy's effects with mathematical precision, but the physical mechanism behind it remains elusive. We can measure its influence on galaxies billions of light years away, but we cannot grasp its substance. One of the striking aspects of dark energy is how subtle yet overwhelming its role is. On human or even galactic scales, its effects are imperceptible. Gravity easily dominates locally, binding stars into galaxies and galaxies into clusters. But on the largest scales, across the immense voids between galaxy clusters, dark energy rules supreme. It stretches the vast cosmic web, thinning out matter and isolating galaxies from one another over time. This invisible energy has transformed our understanding of cosmic destiny. If dark energy continues to behave as it does now, the universe will keep expanding forever, faster and faster. Over billions and trillions of years, galaxies will drift so far apart that their light will never reach one another again. Stars will die, new stars will stop forming, and the cosmos will fade into cold darkness, an outcome often called the Big Freeze.
And yet, despite its overwhelming influence, dark energy remains one of the most enigmatic concepts in science. It's a placeholder for a phenomenon we can observe but not yet explain. A name for our ignorance, wrapped in mathematical precision. The discovery of dark energy didn't close the book on cosmology. It opened a whole new volume filled with questions that reach to the heart of reality itself. From this mysterious force that fills space, one inevitable question follows. Just how much of the universe does dark energy truly make up? To understand the full scale of its dominance, scientists have spent decades mapping and measuring the cosmos, and the results are as humbling as they are astonishing. No one knows exactly what dark energy is, and that mystery makes it one of the most profound puzzles in all of science. We can observe its effects on the cosmos. We can measure how it drives galaxies apart, and we can calculate how much of the universe it seems to comprise. Yet, its true nature remains hidden. What we have are clues, hints, and a few leading ideas, each fascinating, each incomplete. At its core, dark energy appears to behave as a repulsive force, a kind of negative pressure embedded within the very structure of space. Its existence is inferred not from direct detection, but from its influence on the universe's expansion. Whatever it is, it dominates the cosmic energy budget, accounting for roughly 2/3 of all the energy in existence. And to explain such a powerful phenomenon, scientists have proposed two primary possibilities. Either it is a cosmological constant, as Einstein first imagined, or it is a dynamic, evolving field that changes over time. The first and simplest explanation comes straight from Einstein's equations of general relativity. When he introduced the cosmological constant, lambda, in 1917, it was a mathematical term that allowed the equations to balance, effectively giving space an intrinsic energy that counteracted gravity. Einstein discarded it after Hubble's discovery of cosmic expansion, but the 1998 discovery of acceleration brought it back to life. If space itself has a uniform, constant energy density, then as the universe expands, the amount of space increases, and with it, the total energy of the universe increases, driving faster expansion. This model matches the observations remarkably well. In this scenario, dark energy is not a new kind of particle or force, it's a property of space-time itself. Every cubic meter of empty space has the same amount of energy, a small but relentless pressure that pushes everything apart. This fits neatly with Einstein's equations and requires no additional physics beyond what we already know, though it raises an unsettling philosophical question. Why does the vacuum have energy at all? The idea that empty space might not be truly empty is not new.
In quantum field theory, the framework that underpins modern particle physics, even the vacuum seethes with activity. Particles and antiparticles continually pop into and out of existence in fleeting quantum fluctuations. This restless sea of virtual energy is called vacuum energy, and it is believed to pervade all of space. It's tempting to identify dark energy with this vacuum energy. However, there's a monumental problem. When physicists calculate the expected energy of the quantum vacuum, the result is staggering, about 10 to 120 times larger than the dark energy we actually observe. This is not just a minor discrepancy, it is the single largest mismatch between theory and observation in all of physics. It's as if our theoretical model predicted a mountain, but we observe a pebble. This colossal gap suggests that something crucial is missing in our understanding. Maybe quantum field theory overestimates the vacuum energy. Or maybe there's a hidden mechanism that cancels most of it out, leaving only the tiny residual that manifests as dark energy. Or perhaps the cosmological constant isn't the full story after all. That leads to the second major possibility, that dark energy is not constant but dynamic, a changing, evolving energy field that varies across time and space. This idea is often described by the term quintessence, borrowing its name from the ancient Greek concept of a fifth element that filled the heavens beyond earth, air, fire, and water. In the quintessence model, dark energy is a kind of field, similar in concept to the electromagnetic or gravitational field that permeates all of space. Unlike the cosmological constant, it doesn't stay fixed. Its energy density could change slowly as the universe evolves, influencing the rate of expansion in subtle ways. In some versions of the theory, the strength of dark energy might even weaken or disappear entirely in the far future, allowing gravity to regain dominance. In others, it could grow stronger, leading to a catastrophic outcome known as the Big Rip, where the accelerating expansion eventually tears galaxies, stars, planets, and even atoms apart. The advantage of the quintessence hypothesis is that it offers flexibility. It can explain why dark energy's effects only became dominant recently in cosmic history, billions of years after the Big Bang, rather than from the very beginning. It also opens the door to new kinds of physics beyond the standard model, potentially linking cosmic acceleration to fundamental forces we have yet to discover. Still, there is no direct evidence for quintessence or any other dynamic form of dark energy. The observational data so far are consistent with the cosmological constant, a steady, unchanging energy density that behaves exactly as Einstein's lambda predicts. Yet, scientists remain cautious. The universe could be subtly more complex than the simplest model suggests. Even small deviations from constancy could reveal entirely new layers of reality.
There are also other, more speculative possibilities. Some researchers propose that dark energy might not be a form of energy at all, but instead a sign that our understanding of gravity itself is incomplete. Perhaps general relativity, brilliant though it is, doesn't fully describe how space-time behaves on the largest scales. Modified gravity theories, such as f of r gravity or scalar tensor theories, attempt to explain cosmic acceleration not by introducing new energy components, but by tweaking the laws of gravity to behave differently in the vast, low-density expanses between galaxies. Each of these ideas, the cosmological constant, quintessence, or modified gravity, tries to answer the same question. Why does a universe's expansion speed up instead of slowing down? And yet, none of them are fully proven. All remain on the frontier of our understanding. What's clear, however, is that dark energy, whatever its true form, is not a minor feature of the universe. It is the dominant one. It shapes the destiny of the cosmos, governs its large-scale structure, and determines how space and time themselves will evolve. And perhaps most humbling of all, it reminds us that the vast majority of reality, the energy that fills every corner of existence, remains invisible and mysterious. As scientists probe deeper into this mystery, they found that dark energy's influence is everywhere, not just in the distant past or the far reaches of space, but woven into the very fabric of the universe today. To grasp its full significance, we must look at its role in the cosmic balance sheet.
the composition of the universe itself, and see just how much of everything it truly accounts for. When cosmologists began to piece together the full composition of the universe, weighing, in a sense, everything that exists, the results were nothing short of astonishing. All the stars, planets, gas clouds, and galaxies that fill the night sky, everything visible through the most powerful telescopes, turned out to be just a tiny fraction of the total cosmic inventory. The overwhelming majority of the universe is not made of familiar matter at all. In fact, the very fabric of existence is dominated by dark energy, an invisible presence that makes up roughly 68% of the total energy of the cosmos. This conclusion didn't come from a single observation, but from decades of converging evidence. 3 independent lines of inquiry that all pointed toward the same remarkable truth. Dark energy rules the universe. The first came from the supernova observations in the late 1990s, which revealed that cosmic expansion was accelerating. To explain such acceleration, dark energy had to contribute an enormous amount of repulsive energy throughout space. The second came from studies of the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang that still fills the universe today. Detailed measurements from missions like NASA's Wilkinson Microwave Anisotropy Probe, WMAP, and later the European Space Agency's Planck satellite provided a precise snapshot of the universe when it was only about 380,000 years old. By analyzing the tiny temperature fluctuations in that ancient light, scientists could determine how much of the universe's total energy was in the form of matter, radiation, and something else, something invisible that accounted for the majority of the balance sheet. The third line of evidence came from large-scale galaxy surveys, which mapped the distribution of galaxies across billions of light years. These surveys revealed subtle patterns in how galaxies cluster, patterns that can only be explained if the universe's expansion has been influenced by a repulsive force consistent with dark energy. When all 3 methods were combined, supernova, the CMB, and galaxy clustering, they painted a consistent and undeniable picture. About 68% of the universe is dark energy, about 27% is dark matter, and less than 5% is the ordinary matter that makes up everything we know. Those numbers are staggering. It means that every star in every galaxy, every molecule of air, every atom of carbon, iron, and oxygen, all the material that composes planets, nebulae, and life itself, represents less than 1/20th of what actually exists. The visible universe, magnificent as it seems, is only the tip of a vast and invisible iceberg. What's even more humbling is that dark energy isn't just abundant, it's in control. Its influence determines how the universe evolves on the grandest scales. In the early epochs after the Big Bang, matter and radiation dominated the cosmic landscape. Gravity's pull shaped the universe's structure, forming galaxies, stars, and planets. But as the universe expanded, matter became increasingly diluted. The density of matter decreases as space stretches. The same amount of matter spread across an ever-growing volume. Dark energy, however, behaves differently. Its density remains roughly constant no matter how much the universe expands. That means that as the cosmos grows larger, dark energy's relative influence increases. A few billion years ago, matter and dark energy were roughly equal in strength, but as the universe continued to stretch, dark energy took over. Today, it dominates the cosmic balance sheet, and its dominance grows with every passing moment. This shift marks a profound turning point in the history of the universe. For billions of years, gravity, the attractive force of matter, shaped cosmic evolution, pulling gas into galaxies, stars, and planets. But now dark energy has become the driving force. The cosmic expansion is no longer slowing, but accelerating, as dark energy tears vast cosmic structures apart one stretch of space at a time. Galaxies not gravitationally bound to one another are receding at ever-increasing speeds. And in the distant future, most will drift beyond the horizon of visibility, their light stretched into darkness by the relentless expansion of space. To grasp the scale of this transformation, imagine the universe as a cosmic economy. Matter and dark matter are like workers, the ones who build and bind structures, forming galaxies and stars. Dark energy is the unseen banker,
steadily increasing its share of the total wealth until it controls nearly all of it. In the early universe, matter dominated, now dark energy does. And in the far future, its dominance will approach totality. The proportions, 68% dark energy, 27% dark matter, and 5% ordinary matter, come from some of the most precise measurements ever made in science. The Planck satellite, for example, mapped the CMB with exquisite accuracy, giving cosmologists a detailed census of the universe's composition. These results show not only the percentages, but also how each component influences the universe's geometry and destiny. The data reveal that the universe is spatially flat on large scales, meaning that the effects of matter and energy perfectly balance the curvature of space, a result that matches predictions from the Big Bang and inflation theories.
But while we can measure how much dark energy there is, we still have no clear idea what it actually is. Is it truly Einstein's cosmological constant, a fixed energy of the vacuum? Or is it something dynamic, like quintessence, slowly changing as the universe evolves? The numbers alone cannot tell us. They only describe the effects. The nature of dark energy itself remains hidden, an invisible hand shaping the cosmos from behind the curtain. What these discoveries make clear, however, is that dark energy is not a minor player in the cosmic drama, it's the main character. It sets the pace of the universe's expansion, determines its geometry, and dictates its future. Without dark energy, the cosmos would evolve entirely differently. With it, we are living in a universe that is not only expanding, but doing so ever faster, driven by an unknown force that we can neither see nor touch. And yet, as vast and dominant as dark energy is, it acts with delicate subtlety. Its influence isn't felt within galaxies or solar systems where gravity reigns supreme, but only across the immense expanses between them. It doesn't rip apart atoms or planets. It stretches the cosmic fabric gently but inexorably, like a silent wind blowing through the void. Over billions of years, that subtle force accumulates, shaping the destiny of everything in existence. Knowing that 2/3 of the universe is made of something we don't understand forces us to confront a humbling truth. Our most advanced science, for all its achievements, has only begun to scratch the surface of reality. The visible cosmos, all its stars and galaxies, is but a faint shimmer atop a sea of invisible energy. And the deeper we peer into that sea, the more it challenges the very foundations of physics itself. To understand how this unseen energy drives the universe's expansion, we must explore not just how much of it exists, but how it behaves, how it interacts with the expanding fabric of space, and dictates the very tempo of cosmic evolution. Dark energy is a force unlike anything else in the universe, elusive, immeasurable in the lab, yet cosmically omnipresent. Its strange and paradoxical nature lies in how it interacts with the expansion of space itself. While matter grows thinner and more diffuse as the universe expands, dark energy remains constant, or perhaps even grows stronger, ensuring that the expansion doesn't slow down, but instead accelerates. This behavior defies ordinary intuition and sits at the heart of why the cosmos continues to stretch ever faster, even as galaxies drift beyond one another's reach. To understand how dark energy affects the expansion, it helps to first recall how gravity works on cosmic scales. Matter, whether ordinary or dark, exerts gravitational attraction. In the early universe, when matter was densely packed, gravity's pull was immense. It slowed the expansion that began with the Big Bang, working to clump matter together into stars and galaxies. But as space expanded and matter spread out, gravity's influence weakened. The density of matter falls as the universe grows larger because the same amount of mass occupies an ever-increasing volume. Mathematically, matter density decreases with the cube of the scale factor. In simpler terms, if the universe doubles in size, the density of matter drops by a factor of 8. Dark energy, however, plays by entirely different rules. It appears to be an intrinsic property of space, not something contained within it. So when space expands, dark energy doesn't dilute the way matter does.
Each new region of space that forms through expansion carries its own portion of dark energy, with the same density as before. The total amount of dark energy in the universe therefore increases as space grows. This means that, paradoxically, as the universe gets bigger, the influence of dark energy becomes more dominant. This fundamental difference is what drives the accelerating expansion. In the early universe, when matter and radiation were dense, gravity's pull overpowered dark energy's push. Expansion slowed, and matter condensed into galaxies and clusters. But as the universe grew older and larger, matter thinned out. Eventually, roughly 5 to 6 billion years ago, the balance tipped. Dark energy became the dominant term in the cosmic equation, and ever since it has been stretching space at an accelerating rate. We can think of this interplay as a cosmic tug-of-war between gravity and dark energy. For billions of years, gravity led the dance, slowing the expansion and shaping the cosmic web of galaxies. But now, dark energy has taken over as the stronger partner. It is not tearing galaxies apart internally, their local gravity is far too strong, but it is pushing galaxy clusters away from one another, accelerating the large-scale expansion of the universe itself. This acceleration doesn't mean galaxies are moving through space faster than ever before. Rather, it means that space itself is expanding faster between them. Imagine two dots drawn on an inflating balloon. As you blow air into the balloon, the rubber stretches, and the distance between the dots grows. The dots themselves stay put, but the fabric between them increases. Now imagine that the rate of inflation increases with every breath. That's the universe under the influence of dark energy. In a dark energy-dominated cosmos, the effect compounds over time. Because the energy density of space doesn't decrease, but the gravitational pull of matter does, the expansion rate grows exponentially, a phenomenon known as de Sitter expansion. The longer this continues, the more isolated each region of the universe becomes. Distant galaxies recede faster than light, vanishing from view beyond a cosmic horizon. This isn't because they break the laws of relativity, rather, the space between us and them expands faster than light can cross it. Eventually, if dark energy remains constant, the universe will enter a stage of runaway acceleration. On scales of tens of billions of years, galaxies not gravitationally bound to ours will disappear from sight entirely. Even the faint glow of the cosmic microwave background will stretch so far into infrared wavelength that it will become undetectable. The universe will grow dark, quiet, and empty, a cosmic isolation so complete that future observers, billions of years from now, may have no evidence left that an expanding universe ever existed. Yet, there's a subtle nuance here. The details of how dark energy behaves over time are still uncertain. If it's truly a cosmological constant, an unchanging property of spacetime, then the expansion will continue exponentially forever. But if dark energy is dynamic, its effects might evolve. Some models predict that its influence could fade, allowing gravity to reassert itself in the far future. Others suggest the opposite, that dark energy strength could increase, eventually overwhelming all forces, tearing apart galaxies, stars, planets, and even atoms in an apocalyptic Big Rip. Astronomers attempt to constrain these possibilities by measuring a parameter known as the equation of state, symbolized by W, which describes the relationship between dark energy's pressure and density. If W equals -1, dark energy behaves like a true cosmological constant. If W differs slightly, say W is greater than -1 or W is less than -1, it implies a more dynamic nature, possibly pointing to new physics. Current observations suggest W is very close to -1, but not yet known with absolute certainty. Even the smallest deviation could radically alter predictions for the universe's fate.
To measure this, cosmologists use every tool available, from supernovae and galaxy surveys to the cosmic microwave background and gravitational lensing. They're essentially trying to track how the expansion rate has changed over billions of years, comparing the past to the present to infer the behavior of dark energy itself. And although all evidence so far supports the picture of a steady, unchanging dark energy, The quest to confirm or refute that constancy is one of the most urgent in modern physics. The effects of dark energy are subtle on human timescales, but colossal over cosmic ones. It shapes the large-scale geometry of the universe, defines its age, and dictates its ultimate destiny. On local scales, within galaxies, clusters, or solar systems, it is practically invisible, drowned out by gravity's strength. But across intergalactic voids, where matter is scarce and distances are vast, dark energy reigns supreme. It stretches the cosmic fabric, quietly yet relentlessly, ensuring that with each passing billion years, the universe grows emptier, lonelier, and faster. In the end, dark energy may be thought of as the universe's engine of expansion, a hidden force that not only launched the cosmos into motion, but continues to accelerate it, propelling it toward an uncertain future. Whether it remains steady forever or evolves into something more unpredictable, its influence ensures one inescapable truth. The universe we inhabit is not static, but alive, a dynamic, ever-stretching ocean of space-time, flowing endlessly into the unknown. But how do we measure this cosmic acceleration? How do astronomers know with such confidence that dark energy exists and drives the expansion today? The next step in this journey reveals the remarkable techniques humanity has developed to chart the universe's growth across billions of years, from the afterglow of the Big Bang to the flickering light of distant supernovae. Today, measuring the expansion of the universe is one of the most precise and ambitious undertakings in all of science, a grand effort that combines technology, mathematics, and imagination on a cosmic scale. From the faint whispers of ancient light left over from the Big Bang to the violent flashes of exploding stars billions of light years away, astronomers have developed ingenious methods to trace how fast the universe expands and how that rate changes over time. These measurements are how we know that space itself is stretching, that the rate of expansion is accelerating, and that dark energy is the invisible driver behind it all. The story of how scientists measure expansion today is really the story of three complementary cosmic tools: the cosmic microwave background, supernova surveys, and large-scale galaxy maps. Each offers a different window into the universe's history, one peering back to its infancy, one to its Middle Ages, and one to its present-day structure. Together, they form a coherent narrative that allows cosmologists to not only measure the universe's current rate of expansion, but also understand how it has evolved across billions of years. Let's begin with the oldest light in existence, the cosmic microwave background. This faint radiation is the afterglow of the Big Bang, the moment when the universe first became transparent to light about 380,000 years after its birth. When we observe the CMB today, we're seeing a direct imprint of the early universe's conditions, preserved across 13.8 billion years of cosmic time. Its temperature is astonishingly uniform, about 2.7 Kelvin, or just above absolute zero, but contains tiny fluctuations, minute differences in density and temperature that served as the seeds for all cosmic structures that would later form. Satellites like COBE, WEMAP, and most recently Planck have mapped these fluctuations with incredible precision. By analyzing the patterns in the CMB, the spacing and amplitude of its ripples, scientists can infer fundamental properties of the universe: its age, composition, geometry, and crucially, its rate of expansion at various stages. The physics is subtle but profound. Those tiny ripples encode how matter and radiation interacted in the early universe, which in turn depends on how quickly the universe was expanding at the time. From this, cosmologists extract values for key parameters such as the Hubble constant, the current expansion rate, and the relative proportions of dark matter, dark energy, and normal matter. The CMB offers a snapshot of the very young universe, but to measure how expansion has changed over time, astronomers must look at the cosmos across vast distances and ages, essentially at a time lapse of the universe's growth. That's where supernova surveys come in. As we discussed earlier, Type A supernovae serve as standard candles, explosions of known intrinsic brightness that can be used to measure cosmic distances. By comparing how bright a supernova appears with how bright it should actually be, astronomers determine how far away it is. Combine that distance with a measurement of its redshift, how much its light has been stretched by the expansion of space,
and you have a direct probe of how fast the universe was expanding at that specific time. By collecting data from hundreds or thousands of such supernovae at different redshifts, scientists can reconstruct the expansion history of the universe, effectively watching it grow over billions of years. These surveys, carried out by observatories on Earth and in space, provided the first direct evidence that the expansion is accelerating, not slowing. Today, supernova observations remain a cornerstone of cosmology, continually refining our understanding of dark energy's influence in the universe's expansion rate. Yet even these brilliant explosions tell only part of the story. To truly understand the cosmic expansion, scientists also study how galaxies themselves are distributed across space. This is where large-scale galaxy maps and baryon acoustic oscillations, or BASO, come into play. Baryon acoustic oscillations are subtle patterns imprinted in the distribution of galaxies, echoing the sound waves that rippled through the hot plasma of the early universe before the CMB was released. These ancient cosmic sound waves left a characteristic scale, a preferred spacing between galaxies, that serves as a kind of cosmic yardstick. By measuring how this scale appears at different epochs, astronomers can determine how much the universe has expanded since those early times.
Massive galaxy surveys, such as the Sloan Digital Sky Survey, SDSS, the Dark Energy Survey, DES, and the Dark Energy Spectroscopic Instrument, DESI, have mapped the positions of millions of galaxies across billions of light years, revealing the intricate cosmic web of filaments and voids that stretch through the universe. From these data, scientists can track the rate of expansion with remarkable precision and test whether it has remained constant, accelerated, or changed over time. Each of these methods, CMB, supernovae, and galaxy clustering, operates across different eras of cosmic history, yet they converge on the same story. The universe is expanding, and that expansion is accelerating. When the results are combined, cosmologists can construct an extraordinarily detailed model of the universe, known as the LCDM model. In this framework, lambda represents dark energy, modeled as Einstein's cosmological constant, while cold dark matter represents the unseen mass that shapes cosmic structure. Together, these components, along with a small contribution from ordinary matter, explain nearly all of the universe's large-scale behavior. Still, there are intriguing tensions and puzzles hidden in these measurements. When cosmologists use the CMB to infer the Hubble constant, the universe's present expansion rate, they get one value, about 67 kilometers per second per megaparsec. But when they measure it using nearby supernovae and galaxies, looking at the more recent universe, they get a slightly higher number, around 73 kilometers per second per megaparsec. This discrepancy, known as the Hubble tension, has sparked intense debate and could hint that something deeper is going on, perhaps new physics beyond their current understanding. In short, measuring the universe's expansion is a triumph of precision cosmology, a cosmic detective story spanning the entire history of existence. Through light, radiation, and the distribution of galaxies, we've learned not only that the universe is expanding, but that it's doing so faster than ever, driven by an unseen force that fills all of space. And yet, this story of measurement leads naturally to the next great question. How do we quantify the expansion itself? What number captures the rate at which the universe stretches, and why do different methods yield slightly different results? That number, both a symbol of progress and a source of tension, is the Hubble constant, and understanding it is key to unlocking the universe's true age, size, and fate. The Hubble constant, often denoted as h sub 0, is one of the most fundamental numbers in cosmology. It defines how fast the universe is expanding today, setting the scale for everything from its age to its ultimate fate. In essence, it tells us how quickly galaxies recede from one another. For every megaparsec, about 3.26 million light-years of distance, the recessional velocity increases by h sub 0 kilometers per second. But here's the twist. The universe has refused to give us just one simple answer. Over the past few decades, astronomers have developed multiple methods to measure h sub 0,
each grounded in incredibly precise observations and sophisticated physics. Yet, these methods don't quite agree. The discrepancy, small in number but enormous in implication, has become one of the greatest unsolved mysteries in modern cosmology. It's known as the Hubble tension, and it may well be the crack in our current understanding that points toward new physics. To understand this tension, we need to look at the two main ways scientists determine the expansion rate. The first measures the early universe, while the second measures the late universe. Both should yield the same value because, after all, there's only one universe, but they don't. Let's start with the early universe approach. Using the cosmic microwave background, scientists can infer how fast the universe must be expanding today based on its physical conditions when it was just a few 100,000 years old. The Planck satellite, which mapped the CMB with extraordinary precision, found that the data fits beautifully within the standard cosmological model, the LCDM model, where lambda represents dark energy, Einstein's cosmological constant, while cold dark matter represents the unseen mass that shapes cosmic structure. According to Planck's analysis, the Hubble constant is about 67.4 kilometers per second per megaparsec. That value described the universe about 13.8 billion years old, consistent, elegant, and firmly rooted in general relativity and the Big Bang framework. But then came the late universe measurements, and with them, the trouble. In the late universe, astronomers measure the expansion rate directly, using standard candles such as Cepheid variable stars and Type 1a supernovae. These are nearby, well-studied objects whose intrinsic brightness is known, allowing scientists to calculate their distances accurately. By comparing those distances to the galaxy's redshifts, astronomers can directly determine how fast space is expanding right now. The most refined of these measurements come from the SHOES project, supernovae H0 for the equation of state of dark energy, led by Nobel laureate Adam Rees. After years of painstaking observation using the Hubble Space Telescope, the team found a value of 73.0 kilometers per second per megaparsec, significantly higher than the CMB-derived number. Other independent measurements using similar distance ladder techniques, including observations of water masers and red giant stars, have all returned results closer to this higher value. So what's the big deal? A difference of just a few kilometers per second per megaparsec might not sound like much, but statistically it's enormous. The gap between the two measurements, about 5 to 6 kilometers per second per megaparsec, now exceeds 5 standard deviations, 5 sigma, which in scientific terms means it's extremely unlikely to be a mere fluke or measurement error. The Hubble tension is real, persistent, and puzzling.
And this is where the mystery deepens. Both sides, the early universe and late universe measurements, are backed by robust data and sound methods. The Planck satellite's results are incredibly consistent and have been confirmed by independent observations. Likewise, the distance ladder approach has been refined and cross-checked with multiple techniques. There's no obvious error left to blame. That leaves cosmologists with two unsettling possibilities. Either there's an undiscovered systematic bias in the data, or our understanding of the universe's physics is incomplete. If the tension cannot be explained away by errors, then it could be pointing toward new physics beyond the standard cosmological model. For instance, perhaps dark energy isn't a true constant but changes over time, affecting the expansion history differently than we expect. Or maybe there's an additional component in the early universe, sometimes referred to as early dark energy, that altered how quickly the cosmos expanded shortly after the Big Bang, leaving an imprint on the CMB and throwing off our extrapolations. Other ideas are even more radical. Some researchers propose modifications to Einstein's general relativity on cosmic scales, suggesting that gravity might behave differently across immense distances. Others speculate about unknown kinds of particles, perhaps a new species of neutrino or a form of dark radiation that could subtly alter the energy balance of the early universe. Still, it's also possible that we simply don't yet have the precision needed to reconcile the two measurements. Future observatories may refine the numbers further and uncover hidden biases. Projects like the James Webb Space Telescope,
The Vera C. Rubin Observatory and the Euclid mission are poised to make crucial new observations that could finally bridge the gap or widen it, confirming that something truly profound is missing from our picture of the cosmos. The Hubble tension is more than just a numerical disagreement. It's a potential clue that our understanding of cosmic history is incomplete. It's reminiscent of the early 20th century, when unexplained anomalies in planetary motion led to the discovery of new physics, first Einstein's relativity and later quantum mechanics. In the same way, the discrepancy in the expansion rate might be the first whisper of a deeper truth about the universe, one that could transform cosmology yet again. Regardless of how it's resolved, the Hubble tension serves as a humbling reminder. Even as we map galaxies billions of light years away and trace the first light of creation itself, the universe still holds secrets that defy our equations. The cosmos remains dynamic, surprising, and mysterious, and in its silent expansion, it may be hinting at new laws of nature we have yet to imagine. But as we look forward, we must also look far ahead, beyond today's mysteries and measurements, to the question that looms over everything. What will become of the universe itself? If dark energy continues to drive the expansion faster and faster, what will the far future look like? To answer that, we must follow the expansion to its ultimate conclusion, to the fate of all that exists. If the universe continues to expand at its current accelerating rate, as all evidence so far suggests, then the cosmos we know today will one day look utterly different. The majestic tapestry of galaxies stretching across space will slowly unravel, its threads pulled farther and farther apart by the relentless push of dark energy. The night sky, once ablaze with light from countless galaxies, will fade into darkness, and the universe will become a place of isolation, a cosmos of lonely island universes. To understand what the far future might hold, we must imagine time on scales so vast they defy intuition, not thousands or millions of years, but billions and trillions. On human time scales, the expansion of the universe is imperceptible. Galaxies appear fixed, eternal. Yet across cosmic epochs, the cumulative effect of dark energy's repulsive pressure transforms the very structure of reality. In the next few billion years, the Milky Way and its nearest large neighbor, the Andromeda Galaxy, will collide and merge, not because of dark energy, but because their mutual gravity binds them tightly enough to overcome the expansion of space. Together, they will form a new, larger galaxy, often dubbed Milkdromeda. This merging process will repeat for other galaxies in our local group, a small cluster of galaxies held together by gravity. But beyond our local group lies a much larger cosmic landscape, superclusters, filaments, and vast voids, the grand scale structure of the universe. It is across these immense distances that dark energy dominates. The galaxies that are not gravitationally bound to ours are receding at speeds that grow with distance, and as the acceleration continues, the gap between clusters will increase exponentially. In about 100 billion years, most galaxies outside our local group will have moved so far away that their light will never reach us again. This isn't because they'll be moving through space faster than light, but because space itself will be expanding faster than light can traverse it. Beyond a certain distance, called the cosmic event horizon, light emitted today will never reach us no matter how long we wait. Those galaxies will effectively vanish, not because they cease to exist, but because the fabric of space will stretch their light into oblivion, redshifting it to wavelengths so long that it becomes undetectable. As this happens, the observable universe will shrink around us, even as the universe itself continues to expand. The cosmic web, that vast network of galaxies, clusters, and filaments, will fragment. Superclusters will disband. Each gravitationally bound region, like our local group, will become an island universe, drifting alone through the dark sea of expanding space.
For future observers living in those distant times, the cosmos will look profoundly different. Without other galaxies visible in the night sky, the evidence of expansion will vanish. The faint glow of the cosmic microwave background, the afterglow of the Big Bang, will stretch to wavelength longer than the size of the observable universe itself, fading entirely from detection. Future astronomers, even with perfect instruments, will see only their own galaxy and a dark, empty void beyond. In that far future, the universe will appear static and eternal once again, a cruel irony as it will have come full circle to the very misconception that humans held before Hubble's discovery. The truth of the Big Bang, cosmic expansion, and the existence of dark energy will be hidden forever behind the veil of time and distance. The cosmos will have erased its own history. Beyond trillions of years, the changes grow even more profound. The stars that now illuminate galaxies will burn out one by one as nuclear fuel runs dry. New stars will form more rarely and eventually not at all as gas clouds are consumed or ejected. The universe will fade into the degenerate era, filled mostly with remnants, white dwarfs, neutron stars, black holes, and cold planets wandering in darkness. Even black holes, the most enduring of cosmic structures, are not eternal. Through a process known as Hawking radiation, they slowly evaporate, leaking energy back into the universe over inconceivably long timescales. The largest black holes may take 10 to 100 years or more to vanish completely, but eventually, even they will be gone. By that time, dark energy will have stretched space so thoroughly that any remaining particles will be impossibly far apart. The universe will be vast beyond imagination, cold beyond measure, and dark beyond description. All light, all warmth, all structure, gone. The expansion will continue forever, but nothing meaningful will remain to expand into. This distant epoch is sometimes called the Cosmic Dark Age, the final act in the story of existence. A universe that began in blinding brilliance will end in silence. Its energy spreads so thin that no new complexity can ever arise. Time will go on, but change will cease. And yet, even within this bleak vision, lies a strange kind of beauty. The same laws that gave birth to stars and life, the interplay of gravity, energy, and expansion, continue to operate even as their consequences carry existence toward solitude. The universe doesn't end with an explosion, but with a whisper, a gradual dimming into quiet eternity. However, this vision assumes that dark energy remains constant. If it evolves, if its strength changes over time, the future could look very different. Some models predict that dark energy might decay or reverse, allowing gravity to reassert control, possibly leading to a big crunch where the universe collapses back into itself. Others predict the opposite extreme, a big rip, where dark energy's repulsion grows stronger and stronger, ultimately tearing galaxies, stars, and even atoms apart. Each of these possibilities depends on the true nature of dark energy, whether it's Einstein's cosmological constant, a dynamic field, or something entirely unknown. Whatever the case, one thing is certain: the universe's expansion will continue to shape its destiny long after the last light has faded. The cosmos we see today, filled with billions of galaxies, bursting with energy and life, exists in a fleeting, golden age. For now, galaxies still shine, light still travels, and the evidence of the Big Bang still glows faintly across the heavens. But in the far future, that cosmic memory will fade, leaving behind quiet islands in a vast and ever-growing sea. And as we contemplate that distant era, we are left to wonder, if the expansion of the universe continues endlessly, what final fate awaits it? Will it freeze, rip apart, or recycle itself anew? To answer that, we must explore the potential destinies of the cosmos, the ultimate outcomes written in the equations of space and time. When cosmologists gaze into the deep future of the universe, they aren't merely indulging in speculation, they're following the mathematical consequences of the laws of physics as we understand them. From Einstein's relativity to the equations describing dark energy and cosmic expansion, the universe's fate can be traced like a trajectory written in space-time itself. Yet, because we still don't fully understand dark energy, the end of the cosmos remains a branching tree of possibilities. Among the most studied and haunting of these are three grand scenarios: the Big Freeze, the Big Rip, and, less likely, though still conceivable, the Big Crunch. The first and most widely accepted, the one most consistent with what we currently observe, is the Big Freeze, also known as the heat death of the universe. It's not a dramatic ending. There's no fiery explosion or sudden collapse, but a slow, inexorable dimming, a cosmic fading into darkness and cold. In this future, dark energy continues to drive the universe's expansion forever. Space stretches faster and faster, and the density of matter, galaxies, stars, and gas, continues to drop.
As galaxies move farther apart, their mutual gravitational ties weaken. Star formation, which relies on dense clouds of gas collapsing under gravity, gradually ceases as that gas becomes too dispersed. Within about 100 trillion years, the last generation of stars will exhaust its fuel, and the universe will enter what astronomers call the degenerate era. Only remnants will remain: white dwarfs, neutron stars, black holes, and the faint glow of decaying radioactive elements. Over unimaginably long spans of time, even those remnants will change. White dwarfs will cool into black, cold cinders. Neutron stars will fade. Black holes, which dominate this dark cosmos, will slowly evaporate through Hawking radiation, a quantum process that allows them to lose mass bit by bit. The most massive black holes, billions of times heavier than the Sun, may take 10 to the 100 years or more to evaporate completely. After that, after the last black hole flickers into nothing, the universe will be left in a state of near absolute zero. Space will still expand, but it will be empty. Particles will be so far apart that collisions become almost impossible. The cosmic background radiation will stretch to a wavelength so long that even a single photon might span an entire galaxy. Time itself will lose meaning, as no significant events will ever occur again. This is the Big Freeze, not an explosive end, but an eternal stillness, a cosmic winter without end. Entropy, the measure of disorder, will have reached its maximum, and the universe will settle into what physicists call thermodynamic equilibrium. There will be no gradients of energy, no stars to shine, no life to evolve or remember. The universe, once blazing with creation, will fade into a quiet, endless dark. Yet, as inevitable as the Big Freeze might seem, it's not the only possible fate. If dark energy doesn't remain constant, if its strength increases over time, the cosmos could face a far more violent ending known as the Big Rip. In this scenario, the repulsive force driving the universe's expansion doesn't stay steady but grows stronger with every passing eon. As the expansion accelerates, it begins to overpower not just the gravity between galaxy clusters, but the gravity within galaxies themselves. First, distant clusters drift apart, as in the Big Freeze. Then, the expansion reaches the scale of galaxies. Stars are pulled from their orbits, and the Milky Way itself disintegrates. But the process doesn't stop there. As dark energy's influence grows exponentially, it begins to overcome even the forces holding solar systems together. Planets would drift away from their stars. Then, on smaller and smaller scales, the acceleration would overwhelm the electromagnetic forces that bind atoms. Finally, in the universe's last moments, even atomic nuclei would be torn apart. Physicists call this type of dark energy phantom energy, a form with an equation of state parameter W less than -1, meaning its pressure is so negative that its repulsion increases without bound. In such a universe, everything, from galaxies to molecules, would be shredded by the accelerating expansion in a final catastrophic crescendo. If the Big Freeze is a slow fading into silence, the Big Rip is the universe screaming itself apart. Depending on the properties of dark energy, it could happen in tens of billions of years or much sooner. Current observations suggest that dark energy strength is close to constant, but not yet proven to be exactly so. If it even slightly increases over time, the Big Rip becomes a real, if distant, possibility. Then there's the Big Crunch, a scenario that was once the leading theory before the discovery of dark energy turned everything upside down. In this vision, gravity eventually overcomes expansion, halting it and reversing it. The universe would begin to contract, galaxies rushing back together as the cosmic scale factor shrinks. Over eons, temperatures and densities would climb again, perhaps culminating in a final collapse, an inverse Big Bang, where all of space and time condense into a single, searing point. Though current evidence strongly suggests that dark energy prevents such a reversal,
The Big Crunch still captures the imagination because it offers a kind of cosmic symmetry. Some cosmologists have even speculated that a Big Crunch could lead to a new Big Bang, that the universe might be cyclical, endlessly expanding and collapsing, reborn from its own ashes like a phoenix. While intriguing, this idea requires dark energy to somehow change its nature or reverse its sign, something for which there's no clear evidence yet. So, the future of the universe hinges entirely on dark energy's behavior. If it remains constant, the big freeze awaits. If it grows stronger, the big rip will come. If it decays or changes sign, gravity could take over again, leading to a big crunch or a rebirth. Each path paints a different portrait of eternity: endless cold, violent disintegration, or eternal recurrence. What's both fascinating and haunting is that we are living in a cosmic moment when these futures are all possible, but none yet determined. The universe is about 13.8 billion years old, still young on cosmic terms, and its fate remains written in the mysterious nature of dark energy. Whether the cosmos fades, rips, or rebounds depends on a form of energy we've only just begun to detect and cannot yet understand. For now, all we can do is measure, observe, and imagine, watching the expansion as it unfolds, knowing that we're witnessing a single frame in a cosmic film billions of years long. But whatever ultimate fate awaits, it's clear that dark energy is not just shaping the universe's present, it is scripting its future. And as cosmologists continue to explore these grand scenarios, they've begun to ask an even deeper question. What if the very concept of dark energy is a sign that our understanding of gravity itself is incomplete? What if the universe's expansion isn't being driven by an unseen energy at all, but by a fundamental flaw in the way we describe space-time?
This brings us to the next frontier, the alternative theories, where scientists dare to imagine that the universe's acceleration might not come from energy, but from the scripture of reality itself. While dark energy remains a leading explanation for the universe's accelerating expansion, not all scientists are convinced that an invisible, pervasive energy field is the answer. Some researchers have chosen a different path, one that questions the very foundation of how we understand gravity itself. Instead of assuming that some new and mysterious energy fills the cosmos, they ask, what if Einstein's theory of general relativity simply isn't the full story? This line of thinking has led to the development of alternative theories of gravity, frameworks that attempt to explain cosmic acceleration without invoking dark energy at all. The logic behind these ideas is compelling. General relativity, though extraordinarily successful, has been tested mainly within the scales of our solar system, stars, and galaxies. It passes those tests perfectly. But when applied to the entire universe over billions of light years, perhaps its equations begin to break down or require modification. After all, Einstein himself developed relativity over a century ago, long before we could observe the large-scale structure of the cosmos, the cosmic microwave background, or the expansion history we now see. One of the earliest and most studied of these alternative approaches is known as modified gravity, or more specifically, FR gravity. In Einstein's general relativity, the curvature of spacetime, represented by the mathematical quantity r, the Ricci scalar, determines how matter and energy move, and vice versa. The relationship between curvature and matter is beautifully simple and linear. But what if, instead of relying on this linear relationship, the universe obeys a more complex rule, one in which the gravitational action depends on a more general function of r, hence F of r gravity? In these models, gravity behaves slightly differently on large scales than it does locally. At small scales, in our solar system or within galaxies, Einstein's equations still hold, so we see no conflict with observations. But across vast cosmic distances, gravity could weaken or stretch in a way that mimics the effects we currently attribute to dark energy. In other words, the universe might not be accelerating because some exotic force is pushing galaxies apart. It might be accelerating because gravity itself changes behavior at extreme scales. Another approach stems from the idea of extra dimensions, as inspired by string theory and brain cosmology. In these theories, our familiar universe, with its 3 dimensions of space and 1 of time, could just be a brane or membrane floating within a higher dimensional space. Gravity, unlike other forces, might leak into these extra dimensions, subtly altering its behavior on large scales. One popular model that emerged from this idea is the DGP model, proposed in the early 2000s. In the DGP framework, the universe's acceleration arises naturally, because gravity dilutes as it escapes into higher dimensions, producing an effect that looks like dark energy, but requires no additional energy component. There are also theories known as scalar tensor models, which add a new ingredient to the mix, a scalar field that interacts with gravity. In these scenarios, gravity's strength can vary over time or from place to place, depending on how this field evolves. Some versions of quintessence, where dark energy is a dynamic field, overlap with scalar tensor theories, blurring the line between modified gravity and true dark energy models. The distinction often comes down to whether the effect arises from changes in gravity's behavior or from the introduction of a new energy field acting within the existing gravitational framework. A particularly intriguing idea comes from MOND, or modified Newtonian dynamics, and its relativistic extensions such as TeVeS, or tensor vector scalar gravity, originally proposed to explain galaxy rotation curves without dark matter. Though MOND was not developed to address dark energy directly, its underlying philosophy, that our laws of gravity might need adjustment at low accelerations, echoes the same questioning spirit. If gravity doesn't act exactly as we think, it might also explain why the universe's expansion behaves unexpectedly. Even more exotic proposals go further still. Some scientists have explored entropic gravity, which suggests that gravity isn't the fundamental force at all, but an emergent phenomenon arising from the thermodynamic behavior of microscopic degrees of freedom in spacetime. In this view, the universe's expansion might be a large-scale statistical effect, tied to entropy and information rather than energy or curvature. If space and time themselves have thermodynamic properties, then perhaps cosmic acceleration is a reflection of deep underlying principles, not a mysterious form of energy at all. However, despite their creativity and elegance, none of these alternative theories have yet displaced dark energy as the most likely explanation. Observations of the cosmic microwave background, galaxy clustering, and gravitational lensing all fit remarkably well with the LMCDM model, the standard cosmological framework that includes Einstein's cosmological constant as dark energy. Modified gravity theories often face the challenge of matching this level of precision while still producing the correct expansion history and structure formation that we observe. That said, the scientific community continues to test these alternatives rigorously. Upcoming missions such as ESA's Euclid, NASA's Nancy Grace Roman Space Telescope, and ground-based projects like the Vera C. Rubin Observatory will provide unprecedented data about the geometry and expansion of the universe. These observations may confirm the dark energy paradigm or reveal subtle deviations that hint at new gravitational physics. If any of these deviations are found, it would represent a revolution on par with Einstein's own. It would mean that our understanding of space-time, gravity, and perhaps even reality itself is incomplete. But even if dark energy remains the best explanation, the pursuit of alternatives is not wasted. It deepens our grasp of fundamental physics and keeps alive the spirit of scientific humility. For now, dark energy stands as the simplest and most successful explanation for the universe's accelerating expansion. But the quest to understand whether it's truly an energy of space, a sign of new physics, or a symptom of gravity's hidden complexity is far from over. And that pursuit leads us naturally to the most humbling realization of all. For all our equations and observations, we still understand only a fraction of what the universe is made of, and perhaps even less about why it behaves the way it does. As we come closer to the edge of our knowledge, we're left to confront what we don't know and what it might mean for our place in this vast expanding cosmos. For all our progress, for all the telescopes satellites, equations, and deep space measurements, there remains a truth as humbling as it is awe-inspiring. We still don't know what dark energy is. It's the single largest component of our universe, making up nearly 70% of everything, and yet it lies completely beyond our comprehension. We can measure its effects with exquisite precision. We can see how it shapes the cosmos, but its true nature remains hidden, cloaked behind the veil of space-time itself. Dark energy stands as one of the greatest enigmas in all of science, a problem so vast that it touches every corner of physics. It challenges the foundations of general relativity, questions the completeness of quantum field theory, and hints that the universe itself may contain principles we haven't yet begun to imagine. Understanding it isn't just about solving a cosmological puzzle. It could rewrite our understanding of reality. What we know so far is tantalizing but incomplete. Dark energy behaves like a repulsive pressure that drives the expansion of space, counteracting gravity's pull on the largest scales. Observations show that its strength doesn't appear to diminish as the universe grows, suggesting that it's either a property of the vacuum itself or a field whose energy density remains constant over time. But beyond those broad strokes, the details vanish into uncertainty. If dark energy truly is Einstein's cosmological constant, then it's an intrinsic feature of spacetime, a constant energy density that fills the universe everywhere, unchanging and eternal. In that case, our universe's acceleration is simply part of the geometry of existence, as natural as gravity or inertia. But this interpretation brings with it one of the greatest glaring paradoxes in theoretical physics.
According to quantum field theory, even empty space should teem with virtual particles flickering in and out of existence. These quantum fluctuations should contribute to the vacuum's total energy, an energy that, when calculated, turns out to be staggeringly huge, roughly 10 to the 120th times greater than what we actually observe as dark energy. This discrepancy, often called the worst theoretical prediction in the history of physics, suggests that something about our understanding of the vacuum, or of space-time itself, is profoundly incomplete. Alternatively, if dark energy isn't constant, then it could be dynamic, a field that evolves slowly over time. This quintessence idea offers a different path forward, one that might explain why dark energy became dominant only recently in cosmic history. But if dark energy evolves, then we must ask, what is it made of? What rules govern it? How does it interact with gravity and matter? Every possible answer leads to deeper questions, and each question pushes us closer to the edge of known physics. And then there's the possibility, perhaps the most unsettling of all, that dark energy isn't an energy at all, but a sign that our understanding of gravity itself is incomplete. Maybe Einstein's general relativity, brilliant though it is only an approximation, a theory that works beautifully at small and medium scales, but begins to falter on the cosmic stage. If that's true, then solving the mystery of dark energy may require a new theory of gravity, one that unifies the smooth geometry of spacetime with the jittering, probabilistic world of quantum mechanics. For over a century, physicists have tried to reconcile those two frameworks, relativity and quantum theory, into a single coherent description of the universe. Dark energy may be the key that finally unlocks that unification. It may hold the bridge between the cosmic and the quantum, between the vastness of galaxies and the subatomic foam of spacetime. But to get there, we'll need a revolution in physics, one as profound as Einstein's own in 1915. Right now, our understanding of dark energy is descriptive, not explanatory. We can model how it behaves, we can map how it affects the universe's expansion, but we cannot yet say why it exists or what it truly is. Every observation deepens the mystery. The more accurately we measure it, the more it eludes comprehension. It's as if the universe has written its most important equation in a language we're only beginning to learn.
And so scientists continue to search, with telescopes and satellites, with equations and simulations, with imagination and humility. Projects like the Euclid mission and Nancy Grace Roman Space Telescope are now peering deeper into the cosmic past, mapping the shapes of galaxies and the subtle warping of light caused by dark energy's influence. Every new image, every new data set brings us closer to understanding whether this mysterious force is constant, dynamic, or something altogether unimagined. But there's another layer to this mystery, one that reaches beyond science into philosophy. Because dark energy doesn't just raise questions about physics, it raises questions about meaning. We live in a universe where most of what exists is invisible and unknown. The very space we inhabit, the very backdrop of our existence, is alive with forces we can't touch or see. And yet, out of this unknowable darkness, life has emerged, a species of thinking matter capable of questioning its own origins. Perhaps that's the most extraordinary part of the story, that finite beings on a small planet circling an average star can even begin to ask questions about the energy that drives the cosmos itself. We're part of a universe that is expanding, and yet we've developed the capacity to step outside of that motion, to reflect, to measure, to wonder. And in that wondering, we find a strange sense of connection. Dark energy may seem cold and impersonal, but it's the force that shapes our cosmic home, the unseen rhythm behind the great unfolding of space and time. Understanding it may one day transform not just our physics, but our perception of existence itself. Until that day comes, dark energy remains both a mystery and a mirror, reflecting the limits of our knowledge and the vastness of our curiosity. It stands as a reminder that the universe is not static, not finished, but still becoming, still writing its story in the stars. And as we ponder that unfinished story, we arrive at the final reflection, a human perspective on what it all means, what the expanding universe tells us not only about the cosmos, but about ourselves, our fleeting moment within it, and the wonder of being part of something so vast and alive. Standing beneath the night sky, it's easy to forget that we're moving, that the calm, star-strewn dome above us is not fixed, but in motion. Every point of light carried along on an invisible current of expanding space. The universe feels eternal, unchanging, yet in truth, it is alive with motion, with growth, with transformation. The stars we see are drifting apart, the galaxies receding into darkness, and the very fabric of the cosmos is stretching in all directions. We live in a universe that is not static, but still unfolding, a cosmic story still being written. And this realization, that the universe expands, that it evolves, reshapes our sense of place and time in profound ways. For millennia, humanity saw the cosmos as something fixed and eternal, a stage upon which life briefly flickered. But modern cosmology has revealed something far grander and more humbling. We are not living in a static backdrop, but inside a living, changing entity, a universe with a past, a present, and a future. Every moment we experience, every breath, every heartbeat happens in a cosmos that is expanding. The galaxies we see through telescopes are not just distant in space, but ancient in time. Their light has traveled billions of years to reach us, crossing an ever-stretching ocean of spacetime. When we look out into the deep night, we're not seeing what is, but what was. The ghosts of ancient suns, the fossils of cosmic history etched in light. We are time travelers by the simple act of looking up. That alone should stir a sense of awe. But the story of expansion goes even deeper. It reminds us that the universe, vast, cold, and indifferent though it may seem, is not a closed system. It's dynamic, it's creative. Out of the chaos of the Big Bang came order, structure, stars, and life. From the furnace of dying suns came the carbon and oxygen in our blood. We are literally made of stardust, born from the ashes of stars that lived and died long before Earth formed. The expansion of the universe didn't just shape the cosmos, it made us possible.
And now, through science, the universe has become aware of itself. We, fragile beings made of atoms forged in stellar fires, have developed the tools to measure the age of the cosmos, to calculate its rate of expansion, to glimpse its beginning and imagine its end. We are fleeting, but our curiosity connects us to something eternal. We are, in a very real sense, the universe, reflecting on its own existence. When we contemplate the expanding universe, we confront both our smallness and our significance. On one hand, we are infinitesimal, tiny clusters of organized matter, adrift in a cosmos whose scale defies comprehension. Our planet is a speck in a galaxy that is itself a speck among hundreds of billions of others, all receding into the depths of space. Yet on the other hand, we are extraordinary. In this vast and silent universe, we are the observers, the thinkers, the storytellers. The universe has given rise to consciousness, and through that consciousness, it has given rise to wonder. The expanding universe also teaches us about impermanence. Nothing in the cosmos remains the same forever. Galaxies drift apart, stars are born and die, and even atoms may one day decay. But impermanence does not diminish beauty, it creates it. The light of a sunset, the birth of a star, the brief flowering of life. These are transient moments that owe their existence to change. In the same way, our universe's constant expansion is not an end in itself, but a process of transformation, one that continues to unfold across unimaginable scales of time. Perhaps the greatest gift of the expanding universe is the perspective it offers. It tells us that we are part of something vast, ancient, and interconnected, that every atom in our bodies was once part of a cosmic explosion that set space itself in motion. It reminds us that the present moment, brief though it may be, is part of an unbroken continuum stretching back to the dawn of time and forward into an unknowable future. We are passengers on a cosmic tide, born from it, carried by it, and ultimately destined to fade back into it. Yet in the brief span that we exist, we have the capacity to know, to feel, to ask questions that reach the very edge of understanding. That, perhaps, is our greatest connection to the universe, not our physical place within it, but our awareness of it. So when we look into the dark sky and see the faint glow of distant galaxies, we are witnessing more than stars. We are witnessing the history of existence, the trace of everything that has ever been. We are seeing space itself in motion, a silent expansion that began billions of years ago and will continue long after the last light has faded. In that awareness lies both humility and transcendence. The universe will go on expanding, with or without us. But for this brief moment in cosmic time, we are here to see it, to measure it, to marvel at it, to be conscious witnesses to the unfolding of infinity. And that in itself is a miracle. We live in a cosmos still becoming, still stretching toward its future. The expansion that began with the Big Bang continues in every direction, carrying galaxies, stars, and the fragments of our own curiosity along with it. The universe is not finished, and neither are we. Every question we ask, every discovery we make, is part of that unfolding story. The mystery of the expanding universe is not just a scientific puzzle. It's a reminder, a deeply human one, that we are part of a living, evolving cosmos. And as long as we keep looking up, as long as we keep asking why, the universe will continue to reveal itself, one layer at a time, through the light of the stars and the curiosity of the minds that watch them. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.